Have you ever wished you could be in two places at once? Perhaps finishing your work while also relaxing on a sunny beach. It sounds like pure fantasy, doesn't it? In our everyday experience, an object is here, or it is there. It cannot be in both locations simultaneously. This is the reality we have grown accustomed to, a world governed by what we call classical physics. The rules are clear. Objects have definite properties like position and speed. We can predict their movements with certainty, if we have enough information. This is the world of thrown balls and orbiting planets. But what if I told you there is another realm? A place where the familiar rules bend, and sometimes break entirely. This is not a distant galaxy or a fictional universe, it is all around us, it is deep within us, it is the quantum realm. Quantum mechanics is the science that describes this strange and wonderful domain. It is the physics of the very small. Think of atoms, electrons, and photons, the fundamental building blocks of everything. Their world operates on a completely different set of principles, ones that can seem utterly bizarre to our classical minds. The idea of being in two places at once is not just a whimsical thought in the quantum world, it is a genuine possibility. Understanding it is key to understanding everything. Our senses paint a picture of a solid, predictable world. A chair is a chair, a tree is a tree. But if we could zoom in, far beyond what our eyes can see, we would discover a different reality. Everything we touch, see, and are, is made of tiny particles. Atoms are the basic units of chemical elements. They themselves are made of even smaller pieces, protons, neutrons, and electrons. And then there are particles of light called photons. These are the denizens of the quantum world. They are the characters in this extraordinary play. These minute entities do not behave like tiny billiard balls, as scientists once imagined. They are far stranger. An electron, for instance, doesn't always have a definite location until we try to measure it. A photon can sometimes act like a particle, a tiny bullet of light. At other times it behaves like a wave, spreading out through space. This dual nature is one of the first puzzles that quantum mechanics had to confront. It told us that our classical categories of particle or wave were not sufficient to describe reality at this scale. The physics of Isaac Newton, which so beautifully describes the motion of planets and apples falling from trees, simply breaks down at this tiny level. Classical physics predicts that electrons orbiting an atom should radiate energy and spiral into the nucleus. But atoms are stable. One of the most mind-bending concepts in quantum mechanics is called superposition. Imagine you toss a coin. While it is spinning in the air, is it heads or tails? In our classical world, we would say it is definitely one or the other, even if we don't know which until it lands. But a quantum coin is different. A quantum particle, like an electron, can be in a superposition of states. This means it can be, in a very real sense, in multiple states at once. It is not just that we don't know its state. Its state is genuinely a blend of possibilities. Think of an electron's spin. It can be spin up or spin down. In superposition, an electron can be both spin up and spin down simultaneously. It is not half up and half down, it is fully both, existing in a kind of probabilistic haze of all its potential states. This is not simply a matter of our ignorance. The particle itself is in this combined state. It is a fundamental feature of its existence before we interact with it. This idea shatters our everyday intuition that things must be one thing or another. When we try to measure the particle, something remarkable happens. Perhaps the most famous, and arguably the most baffling demonstration of quantum weirdness, is the double-slit experiment. It is simple in concept, yet profound in its implications. Imagine a barrier with two narrow parallel slits cut into it. On one side, we have a source that fires particles, say electrons, one by one towards the barrier. On the other side, there is a detector screen that records where each electron lands. What pattern would you expect to see on the screen? It seems straightforward enough. If electrons were like tiny bullets, we would expect to find two distinct bands on the screen, directly behind each slit. Some electrons would go through the top slit, some through the bottom. They would pile up in two lines. This is the classical prediction, but this is not what happens when the experiment is performed with quantum particles like electrons or photons. Instead of two bands, the screen shows an interference pattern. This is a series of many bright and dark stripes, a pattern characteristic of waves interfering with each other. How can this be? An interference pattern arises when waves pass through both slits simultaneously. The wave from one slit interferes with the wave from the other. Section 5. Spooky connections. The mystery of entanglement. If superposition stretches our understanding of reality, then quantum entanglement takes it to a whole new level of strangeness. Entanglement describes a situation where two or more quantum particles become linked in such a way that their fates are intertwined, no matter how far apart they are separated. They behave as a single system, even if one particle is on Earth and the other is light years away on a distant star. Their individual properties are not definite until measured, but they are perfectly correlated. Imagine you have two entangled electrons. Let's say they are entangled in terms of their spin. One must be spin up and the other spin down, but you don't know which is which until you measure one. If you measure the first electron and find it is spin up, you instantly know that the other electron, wherever it may be, is spin down, and vice versa. It is as if the particles are communicating with each other instantaneously, faster than the speed of light. Section 6. Whispers across the void, quantum communications promise. While Einstein found entanglement spooky, modern physicists and engineers see it as a resource with incredible potential. This peculiar quantum link, where particles remain connected across vast distances, is not just a curiosity for theorists. It is paving the way for revolutionary new technologies, particularly in the field of communication and information security. The very properties that make entanglement seem strange are the ones that can be harnessed for powerful applications, leading to systems far more secure than anything we have today. The most prominent application is quantum cryptography, specifically quantum key distribution, QKD. Imagine two parties, Alice and Bob, who want to share a secret key to encrypt their messages. They can use entangled particles to generate this key. If an eavesdropper, Eve, tries to intercept and measure the entangled particles to learn the key, her actions will inevitably disturb the delicate quantum entanglement. Section 7. The Dawn of Qubits. Powering the Quantum Revolution. The strange rules of the quantum world are not just for understanding the universe, they can be harnessed to build entirely new kinds of computers. Classical computers, the ones we use every day, store and process information using bits. A bit is a simple switch. It can be either a 0 or a 1. All the amazing things our smartphones and laptops do are built upon vast numbers of these simple binary states. But quantum computers are different. They use qubits, which stands for quantum bits. A qubit, like a quantum particle, can exist in a superposition. This means a qubit can be a 0, a 1, or a combination of both 0 and 1 at the same time. This ability to exist in multiple states simultaneously allows quantum computers to perform many calculations at once. Imagine a classical computer trying to find its way through a maze. It would try one path, then another, sequentially. A quantum computer, thanks to superposition, could explore all possible paths through the maze simultaneously. This opens up an incredible potential for computational power. Section 8. Reshaping Reality. Quantum Mechanics and Our Universe. The advent of quantum computing, powered by qubits and their strange properties of superposition and entanglement, promises to reshape many fields. In medicine, quantum computers could simulate molecules with unprecedented accuracy, leading to the rapid discovery of new drugs and therapies. In materials science, they could help design novel materials with specific desirable properties. Artificial intelligence could be revolutionized by quantum algorithms capable of learning and optimizing in ways currently unimaginable. Financial modeling could become far more precise, and complex logistical problems could be solved efficiently. However, this immense power also brings challenges, particularly in cybersecurity. Many current encryption methods rely on the difficulty of factoring large numbers. A sufficiently powerful quantum computer could, using Shor's algorithm, break these codes relatively easily, rendering much of our current digital security obsolete. This is why the development of quantum-resistant cryptography is also a vital area of research, ensuring we are prepared for a quantum future.